So let's relook at the optimization problem we have and understand how it behaves in certain situations. The optimization problem we have is this: W star equals to argmin of, or find the W that minimizes, summation over all the points in the training data, log of 1 plus exp of minus yi w transpose xi, right? This is the optimization problem we have. Let's just, it's slightly tedious to write yi w transpose xi always. So let's just say let zi be equal to yi w transpose xi. Okay, not minus, zi is just this. Then how can I write this problem? I can write this problem as argmin of w, summation over all the points, log of 1 plus exp of minus zi, right? I'll use zi from now onwards. So that zi is nothing but yi w transpose xi, or it's a sign distance, right? Geometrically speaking, right? Now let's look at this term in more detail, right? What do we have? We have log of 1 plus exp of minus zi, right? So summation, of course, over all the i's, right? Now if you notice that there is an interesting thing here, right? Let's take this first part, exp of minus zi, right? Let's take this part, exp of minus zi, and let's plot it. How does a plot of exp of minus zi look like? So I have it plotted here, exp of minus x, right? So if this is my zi, if this is my zi, this is my exp of minus zi, right? It's always positive. Notice that exp of zi, if this is my zi, right? It's always positive. For whatever value of zi I take, exp of minus zi is always positive. That's what I wanted to show, because this plot never crosses this, never crosses the x-axis and comes to this, right? So the first thing to notice is exp of minus zi is greater than equal to 0, right? So this term here is greater than equal to 0 always for all zi, whether zi is positive or not, right? Now let's look at the larger term. What is the larger term here? Log of 1 plus exp of minus zi, right? We just said that this term here is always greater than equal to 0. Then what happens to log of 1 plus something that is greater than equal to 0? Remember, log of 1 is 0, right? So log also has this nice property that log is a monotonically increasing function, right? Log is a monotonically increasing function. So if you add anything to this, so log of 1 plus something, so let's say log of 2 is greater than log of 1, okay, right? So log of 1 plus something which is positive is always greater than equal to 0, because log 1 equals to 0, okay? And we know that log of 1 plus some delta is always greater than equal to log 1 if delta is a positive number, right? Because log is a monotonic function. We saw this many times, right? Log is a monotonic function. As x increases, log of x also increases. I just use this formula here to get log of 1 plus exp of minus zi is greater than equal to 0. Now if each of these is greater than 0, the sum of all of them will also be greater than equal to 0, right? So if you look at our optimization problem is I equals to 1 to n log of 1 plus exp of minus zi. Now this whole sum is always greater than equal to 0, because each of these elements, for each zi, this value is greater than equal to 0. So the total sum is greater than equal to 0, right? So if you take our optimization problem was find the w star that minimizes this whole term. And what is the minimum value? We just discovered that the least value that this term can take, right? What is our optimization problem? Our optimization problem is find the w that minimizes this whole thing. And we just showed right now this whole term here, the summation of this whole term here, the least value that is possible is 0, right? So the least value, the minimal value of summation of I equals to 1 to n log of 1 plus exp of minus zi is 0. Because we just proved it. The smallest possible value that it can take is 0. Now, when does that 0 occur? That's the next question, right? So we just showed right now the minimal value is 0, but when does that 0 occur? So let's assume, so let's take this problem, right? When does that 0 occur? So let's write our optimization problem again, right? Our optimization problem is minimize or argmin, right? W star equals to argmin summation of I equals to 1 to n log of 1 plus exp of minus zi. Now if zi is positive, okay, so let's look at exp of minus zi, right? Let's look at that fun. So exp of minus zi will become 0. Look at exp of minus zi. As zi increases, exp of minus zi decreases. So as zi tends to infinity, right, exp of minus zi also tends to 0, right? As zi is increasing, exp of minus zi is decreasing, right? So what happens is, if zi is positive, and it has to be positive, right? This is where the values fall. If zi is positive, which means if it is in this area, and if zi tends to plus infinity, not minus infinity, then exp of minus zi will tend towards 0. Think of it like limits, right? From plot you can see it, right? As zi increases, as zi goes towards infinity, exp of zi will go towards 0, right? Now as exp of zi goes to 0, log of 1 plus exp of minus zi, this is becoming 0, right? This is becoming very close to 0. So log of 1 plus something which is 0 is, so this will tend to 0 now, because log of 1 is 0, isn't it? And we showed that this whole term, the minimum value is 0. So if zi, so this whole term, the minimal value, so we said that the minimal value of this whole term is 0, and it occurs when zi equals to, or zi tends to infinity. For all I. That is important. When zi tends to infinity for all I. Because if one term is equals to 0 and other term, because there's summation here, right? If one term equals to 0, other terms may not be, right? So zi should tend to infinity for all I. Only then the minimal value occurs, right? This is important. And let's understand what is zi again. Let's not forget the basics. What is zi? Zi was yi w transpose xi. Remember, yi and xi are already given to us in the training data, right? What is the training data? Xi comma yi pairs, right? I equals to 1 to n. So yi and x are already given to us. So if I want to make zi to plus infinity, what should I be doing? I need to now make my w's, right? I need to make my w. I need to modify my w. In such a way that each zi tends to infinity. Plus infinity, not minus infinity, plus infinity. And remember, when zi tends to plus infinity, which means it is positive. And what does it mean when zi is positive? What does this mean when this is positive? If this is positive, it means my point is correctly classified, right? Because this is the sign distance, right? So when zi is positive, it means my point is correctly classified. My xi point is correctly classified. Okay, first thing, when zi is positive, then my point xi is correctly classified by w. 2, if zi tends to infinity, okay, if zi tends to plus infinity, then I will reach my minima. Remember, the optimization problem we're trying to solve is to minimize this term. And what is the least value that it can take? The least value it can take is 0. And when does that happen? When zi's tend to infinity. And how do I modify my zi's? Because within zi's, look at it. Zi's, yi is fixed and xi is fixed because they're coming from training data, right? Because they're coming from dtrain. The only thing that is variable is w. So if I pick my w such that, number 1, all training all training points are correctly classified, perfectly classified actually, are perfectly classified. Number 2, right? If all my training points are perfectly classified, and if all zi's tend to plus infinity, then such a W is the best W. Then we get the best W. But there is a problem with this. It will give you best W, but there is a problem with this. The problem is as follows. What if some of your training points are incorrect? What if some of your training points are outliers? Right? You're basically, if all your training points are perfectly classified whatsoever, whether they're outliers or not, such a thing is called overfitting, isn't it? What is overfitting? Overfitting basically means that you're doing a perfect job, on training data, which doesn't guarantee that you'll do a good job on test data, by the way. It doesn't necessarily mean that, right? So that's a problem we have. So if we have zi's tending to infinity, right, we will get a best W. But to get zi to tend to infinity, your W's also will tend to plus infinity or minus infinity, right? Because if they have to tend to infinity, look at it. What is zi? Your yi's are fixed, xi's are fixed. If zi has to go to plus infinity, if your zi has to go to plus infinity, your W's, your each value in W either has to be plus infinity or minus infinity based on the sign of yi and xi. Right? Based on the signs of these two, it has to be plus infinity or minus infinity. Isn't it? So what is effectively happening is we are overfitting. First thing, we are overfitting. Second thing, my W, my vector, each component of my W either tends to plus infinity or it tends to minus infinity, which means W's are becoming very, very large. Your Wi's, W is a vector. Remember that. Remember that W is a vector with the ith component here. So it is possible, given this optimization problem, given the current state of optimization problem, given this optimization problem that we have, it is possible that if I make my Wi's tend to plus infinity or minus infinity, right? If I make them very large, given a training data of endpoints, I can do perfect fitting. Literally, I'm overfitting, right? Perfect fitting on training data sometimes means overfitting. So it is possible that when I have these two, I will get the least possible value for this optimization problem, which is 0. We showed this, right? The least possible value for this is 0. So how do we control for it? That sometimes happens, not always, but I can construct data sets for which your Wi's become plus infinity or Wi's become minus infinity. Right? And your optimization problem minima value, the minima value becomes 0. Right? How do we not let that happen? While constructing our whole optimization problem, we missed one key aspect. Which is the W is a normal. Okay, that W is a normal to a hyperplane. And what does normal to a hyperplane mean? Normal to a hyperplane basically means that it has W transpose W equals to 1. We didn't use this anywhere. Right? That's one key aspect that we did not put it in our optimization problem. To get rid of all of these problems, there is an idea called regularization in optimization. To get rid of these problems, because if you just try to solve this optimization problem that we started off with, if you try to solve this problem, it's very easy for Ws to become plus infinity or minus infinity, such that each Zi will tend to infinity, and you would overfit to the training data. It's very, very easy for that to happen. To avoid that from happening, we'll modify this optimization problem using regularization. What we do is this. It's a very nice hack. What we'll do is this. We'll say W star equals to argmin of W, right? Summation of I equals to 1 to n. This part remains the same. Log of 1 plus exp of minus yi W transpose xi. This is minus zi, right? To this part, I will add one more term, which is called plus lambda times W transpose W. Let's understand what this is. Okay, let's understand what this is in some detail. This is called L2 regularization. I'll explain you why it's called L2 regularization. This whole thing is exactly what we have. This is what we had for a long time. This is a new part. Let's understand what this part means. This part is nothing but lambda times. What is W transpose W mean? It means summation of I equals to 1 to D or J equals to 1 to D Wj square. Right? What is W transpose W? Right? If you have a vector like W here, what is W transpose W? You'll multiply this with this, you'll multiply the second term with the second term, and so on and so forth. This is nothing but this, right? This is also written as, you can also write it as W L. This is the second norm, the L2 norm of W square. This is nothing but this, right? This part, only this part, right? So let's focus on the second part here a little. What is the second part? Lambda times W transpose W, which is nothing but lambda times J equals to 1 to D Wj square, or this can also be written as lambda times the 2 norm of W square. This is by definition, right? This is the L2 norm. This is the square of L2 norm of W. Now let's understand what happens when we do this. When we do this, right, when I say lambda times Wj square, this will ensure, now because remember, this is a minimization problem. We're trying to minimize the sum of these two things now. We are not just minimizing this part. Please note that we are not just minimizing this part. We're minimizing this plus this. Now, by doing this, your Wj, if it becomes plus infinity, or if Wj becomes minus infinity, this will not be allowed because you're trying to minimize. If Wj becomes infinity, Wj square also will become infinity. And the optimization system will not let it do. Because if it's infinity, it's a maximum value you can reach, right? So in a way, imagine, so we'll come to lambda in a little while. Let's forget lambda for a while. Just let's look at this first term here. So by just adding this term, what's happening here is this term, it'll avoid Wj's from becoming plus infinity or minus infinity. And when they cannot become plus infinity or minus infinity, what happens? When they cannot become plus infinity, so by adding this term, this is called the regularization term. This is called the regularization term in optimization. And this term is called the loss term. We'll come to the loss term understanding a little more when we see the loss function interpretation of logistic regression. For now, this first term is called the loss term. The second term is called the regularization term. So what is the regularization term doing? It's avoiding Wj's from becoming plus infinity or minus infinity. Because if they become very large, right? Because if you look at it like this, right? If Wj's become very large, so this is like a tussle that happens, right? So you have two pieces. The first piece is this. Your first piece is minus Zi, right? Your second piece is summation J equals to 1 to D Wj square. Okay, so what's happening here is when Wj, look at it, when Wj's become plus infinity or minus infinity, this will become very small. You're trying to minimize this whole thing. You're trying to minimize the sum of these two. When this becomes 0, this will become 0, but this will become very, very large, which will not be allowed, right? If W's become very small, right? So first of all, what's happening here? We are getting rid of this problem because we're trying to minimize, right? When you're trying to minimize, if you do not have this term, it's not controlling. This is like a tug of war that's happening. As W's become plus infinity or minus infinity, as they move towards infinities, either the plus infinity or minus infinity, this term will reduce, but simultaneously this term will increase. As this term increases, it will not let it move in the direction. Think of it like a tussle, like a tug of war that's happening between these two terms. These two terms are weighing one against the other. So this is saying, okay, let me make my Wi's plus infinity or minus infinity so that I can reach the minimal value. This is saying, no, I won't let you do that. I will control W's to be more sensible values. right? So that's what it's happening. So the regularization term, and the loss term are literally fighting a tug of war to avoid your zi's to go to, they're avoiding your zi's to go to plus infinity, right? That's a tug of war that's happening, and they will meet at a sweet spot. In a tug of war, there'll be an equilibrium that they will reach. They'll reach a nice point where both this term is small and this term is small, and that's where they will converge to in this optimization problem, right? But they avoid the problem of your w's becoming plus infinity or minus infinity. So in this optimization problem, that we are solving, right, summation I equals to 1 to n log of 1 plus exp of minus yi w transpose xi, right, plus lambda times w transpose w, right? So your regularization term, then you might ask, what is lambda here? Lambda here is the hyperparameter. It's not given to us. So think of it. So we've seen other hyperparameters, right? In k nearest neighbor, what is the right k? K is the hyperparameter. What is the right k? We determined it using cross-validation, isn't it? Similarly, in Laplace smoothing, right? In our naive base, how do we find the right alpha? Alpha was the hyperparameter, right? And we found it using cross-validation. Similarly, the lambda here is the hyperparameter, in logistic regression. Now let's see what happens if lambda equals to 0. If lambda equals to 0, there is no regularization term. Whatsoever. Then what happens? Then you will overfit, right? Then you will overfit, as we saw. We'll overfit to the training data. By trying to make each zi go to plus infinity, right? So if lambda equals to 0, you're going to overfit, right? If lambda equals to infinity, what happens? If lambda is very large, okay, if lambda, let me not call it infinity. If lambda increases, what happens? Then the influence of this in the tug of war decreases. Right? So remember, it's a tug of war that's happening between your loss function and your regularization. So the influence of this will reduce when lambda is very large, and only this will matter. Right? When only this will matter, you are not using your training data anymore. Remember, in the second term, there is no training data. There are no xi's and yi's. When lambda becomes very large, the influence of the loss term reduces, which means you're no more using training data to find the best w. When you're not using training data to find your best w, what happens? You're going to underfit. Right? Just like k nearest neighbor. In k nearest neighbor, if k is very large, what are you going to do? You're going to see whichever is the majority class and call it the class for every query point, isn't it? So similarly, lambda here is a hyperparameter. And when lambda equals to 0, this whole regularization term goes away and you're going to overfit. When lambda is very large, you're going to underfit, because this term will no more, the loss term will have no more influence then. Right? The tug of war here is between the loss function and the regularization function. So a lot of optimization problems in machine learning, you look at things like this. You'll say minimize loss function over training data, okay, plus regularization. This is what you will see as a form of lot of problems in machine learning. You'll minimize loss function over training data plus regularization. That's what it is, right? This is the loss function over training data, and this is the regularization term. You'll see this pattern emerging over and over again in lot of algorithms that we will see in machine learning, right? This is just one example, right? I hope I made myself very clear. And just to quickly recap, when lambda equals to 0, what do we have? When lambda equals to 0, we have an overfit problem, right? And we know how to connect overfitting and underfitting to bias and variance, right? When lambda is very large, right, we are going to underfit. And just to quickly recap, underfit basically means high bias, overfit basically means high variance. And how do we find the right lambda? Through cross-validation. right? How do you find the right lambda? We find it using cross-validation. Again, the same concepts that we learned in when we're doing k nearest neighbor. We do the same cross-validation, either k-fold cross-validation or simple cross-validation. So lambda is the hyperparameter that controls overfitting and underfitting. It is exactly same as the k nearest neighbors k and Laplace smoothings alpha.